Hello and welcome back. Today we're getting into chapter 1. We just had to hit the 2 sections in the appendix before we did that. So 1.1 we get into distance, midpoint, a little work with graphing utilities, and an intro to graphing equations. So just a quick little mini review on the different names that we have for the XY plane, also called the Cartesian plane, also called the rectangular coordinate system, and those are really all just talking about the same thing. It's different names for just the graph that you've been working with all along. So there's just sort of a rough stamped version of one. We just have, remember, just 2 number lines, one horizontal, one vertical, the x-axis and the y-axis. We're broken into 4 quadrants, quadrant 1, quadrant 2, quadrant 3, quadrant 4. And where they meet is, of course, referred to as the origin. 0 on the x-axis number line, 0 on the y-axis number line. So all of that should be reviewed, just a little bit of vocab in case it's been a little bit. As far as some work with graphing utilities, I am currently working with an 83. Most of you probably have 84s. They're pretty similar. Try to just make sure I'm closer to the light here without too much reflection. Try to find that balance there. So if we want to sketch a graph on here, go to your y equals screen, hit clear on any functions that might have been in there before, and we'll start with something like x squared minus 43. Zoom lets you select what window you start with. The standard window is -10 to 10 on each axis. That's what my handy dandy little stamp here is as well. So notice we're missing a chunk of our graph. You remember from your 100 days or whatever equivalent you took somewhere else, an x squared graph should give you the parabola, that classic sort of U-shaped curve. Knowing we expect the vertex to be quite a bit further down, we can adjust this window. So the window key right next to your y equals key. The x's seem to be doing okay for this one, so I'll leave them at -10 to 10. The y min, pardon me, we'll set that down to -45 instead of -10. Max, we'll keep it at 10, and instead of counting by ones, we'll have hash marks, let's say maybe every 5. And we'll hit graph, and it'll put in the new parameters. So now I have all of sort of the key points on the screen. So you will occasionally have to adjust your window when we're graphing something. So again, the important keys that we use, the y equals key, the zoom key, and zoom 6 is the one that we usually start with. So that is x on -10, 10, y on negative 10, 10, with a scale of 1 on each. And we just kind of adjust it as needed from there. All right, so that's how to sort of adjust your window. One of the other sort of hodgepodge of topics that got tossed together into section 1.1 was distance. And with distance, really all you have to do is remember our dear friend Pythagoras. The ancient Egyptians kind of knew this before Pythagoras, but he was the one that slapped his name on it, and his name ended up sticking. Whatever ancient Egyptian mathematician didn't start calling it his name and promote it that way. So that's why we call it the Pythagorean theorem and not whoever it was that was the first to stumble on it. So if you'll recall, and again, you'll see many times this semester why I'm not an art teacher. Leg, we'll call that length A. Another leg of a right triangle, we'll call that length B. And our hypotenuse, sometimes called C, it's also going to be our distance. So if we're looking for a distance between 2 points, we can always basically just sketch in a little right triangle and use our Pythagorean theorem. And the relationship between them, leg squared plus leg squared, is hypotenuse squared. So then the distance is just the square root of the sum of the legs. You don't have to memorize the formula, really just kind of sketching it out is sufficient. So let's consider point 1, point 2, and point 3, given point 1 is 3, 8, point 2 is 9, negative 5, and point 3 is negative 4, negative 11. So we'll start with finding the distance between point 1 and point 3. So I'm just going to make a quick rough sketch of point 1 and point 3. So point 1 is at 3, 8, so we're somewhere in Q1, a little bit higher than we are to the right. Point 2, 9, negative 5, we're in Q4. So this distance is what I'm looking for. I just make that the hypotenuse of my right triangle. So I just drop a line straight down, line segment I should say, and a line segment straight across. So these, I'll have them meet at a nice pretty right angle. So this point shares an x coordinate with this top guy, so 3, and a y coordinate with this bottom guy, negative 5. So the distance, we'll call that C, is what we're after. We'll notice the y's are in the same spot, so just from 3 to 9 is 6 units. Up here, the x's are the same, they're both at 3's, but the y's change from negative 5 to positive 8, so that is 13 units. So 13 squared plus 6 squared is our distance squared, c squared or d squared, use whichever one. So 169 plus 36, that's an ugly 3 there, apologies, is d squared. So d squared is equal to 205. So our distance is square root of 205. Now when we have something underneath the square root, we want to make sure that if we have any perfect square factors, we pull those out. However, 205 is 5 times 41. Those are both primes, so our distance stays written this way. So distance between point 1 and point 3 is root 205. So next up, we'll try the distance between points 1 and 2. So again, I'll do just a quick rough sketch. So point 1 is still at 3, 8. Point 2, we just did, that was, my apologies, that was point 2 that we just did. Point 1 and point 2. So point 1 and point 3 is what we'll work on now. So point 3 is at -4, -11. So over here in Q3. And again, I want the distance. All I have to do is turn that into a nice, neat, pretty right triangle. X coordinate is still at the 3, Y coordinate is now at the -11. So from -4 to +3 is 7 units. From -11 to +8 is 19 units. And here is our distance. So distance squared is 7 squared plus 19 squared. So distance squared is equal to 49 plus, I'll just double check that, yeah, 361. So distance squared is 410. So distance is square root of 410. We don't need the plus or minus that we would usually need when we take the square root of both sides, because distance is never a negative value. So 410, 2 by 5 by 41, so no non-trivial perfect square factors. We can always, of course, grab the trivial one. So this is as simplified as I can get. All right, so we did 1 and 2, 1 and 3, so I'm going to ask you to try the distance between point 2 and point 3. Just a reminder of what those points were. Point 2 was 9, -5. Point 3 was the -4, -11 we just saw. So go ahead and pause that, see if you can find the distance. Okay, welcome back. So just a quick rough sketch here. So 9, -5, we're in Q4, sorry, Q4. -4, -11, we're in Q3. And we want the distance between those two. So we draw our little triangle here. So this guy is at 9, -5. This guy is at -4, -11. So that means this other vertex is an x coordinate of 9, a y coordinate of -11. So from -11 to -5 is 6 units in length. From -4 to +9 is 13 units in length. And there's our distance. So distance squared is 6 squared plus 13 squared. Distance squared. 36 plus 169. So distance squared. 205. So distance is root 205. So some information that we can do knowing these distances. We can see if the 3 points form a right triangle or don't form a right triangle. If they form a right triangle, then we have to have that relationship of a squared plus b squared equals c squared. So our distances that we had one side that had a distance of root 205, another side that had a distance of root 205, and another side had a distance of root 410. We take the smaller two and make those the hypothetical legs. So we see if root 205 squared plus root 205 squared is equal to root 410 squared, and sure enough, square and square root will drop, so we have 205 plus 205 also equal to 410. 410 equal to 410. Since this was a true statement at the end, then the answer is that yes, this is a right triangle. If we did that same work, smallest length squared plus smallest length squared, and got something different than longest length squared, we would have proven then that it was not a right triangle, since it didn't follow the Pythagorean theorem. Since it is a right triangle, we can also pretty easily find the area. Remember, the area of a triangle is just 1/2 times the base times the height. So the area of this triangle would be 1/2 times, one leg was root 205. The other leg was also root 205. So our area would be half of 205. So area 205 half, 205 half square units. The area is always in square whatever, square feet, square miles, square yards, etc. All right, so another concept they have us working on in this section is the idea of midpoint. The midpoint, just think of calculating your average on a couple of assignments. If you get, let's say, 100% on one and 90% on the other, then you have, assuming equal weight, a 95% average on those two. All you need to do, find a midpoint of 2 points, add them up and divide by 2. It's just finding an arithmetic mean. So -6, 14, and -11, -6. And I want the midpoint. So our midpoint, I would just take my x's, add them up, and divide the answer by 2. I would do the same thing with my y's. And that is our midpoint. So -17 halves, 8 halves is 4. Negative 17 halves is also, you could also think of it as negative 8 and 1/2, positive 4. And that should fit. Negative 8 1/2 is in between the negative 11 and negative 6. Positive 4 is between the negative 6 and the 14. So it does generally fit with what we expect to see. All right, so the next thing we get into is sketching a graph using ordered pairs. In other words, plotting points. So we'll try, let's say x cubed plus 2x is equal to y. If one variable is already by itself, plug in numbers for the other one. If neither one is by itself, then we have a little bit of work to do. So if they say plotting points, that basically means plugging and chugging. So picking out, in this case, I'm picking out x's and finding y's. So y is x cubed plus 2x. So here y is 0 cubed plus 2 by 0, which is 0. So this one goes through the origin. X is 1, y is 1 cubed plus 2 by 1. 1 and 2 is 3. Add 2. 2 cubed plus 2 by 2. So we have 8 and 4, 12. So that's kind of already off of our grid a little bit. So then I'll start moving in the other direction. When you're plugging in the negatives, the parentheses go from being a good idea to being a requirement, since you could get different values that way. So negative 1 cubed is still negative 1, 2 by negative 1 is negative 2, negative 1 minus 2, negative 3. If we draw out negative 2, negative 2 quantity cubed plus 2 by negative 2. So we have negative 8 minus 4, negative 12. So negative 2, negative 12 as well. Now we can also pick out some other values. We would just not get nice, neat, pretty integers in there. Or we can also simply scale the graph a little bit. So we go through the origin, and on this one, I don't want to draw a curve with just 3 points. That's not enough to draw a curve. So I'll include the 5 points. So on the y-axis, we'll count by 2's instead of counting by 1's. And well, as long as I have the stamp, let's put it to work for us. So we'll ignore. There we go. Okay, so the vertical axis, we're scaling by 2's. X scale is still 1. So the origin, we go through there. We have 1, 3, so 1 for the x, and the scale is still 1. And remember, each of these is 2. So here's 1, here's 2, here's 3. And at 2 for the x, we're at 2, 4, 6, 8, 10, 12. And we have the same thing happening down in Q3, negative 1, negative 3, so negative 1, 2, 3. Halfway in between the two, and negative 2, negative 2, 4, 6, 8, 10, 12. So we connect it up with a smooth curve and arrows on the end. A lot of books don't include the arrows. They really are necessary. They do mean that this pattern goes on. So you do want arrows on the ends of your smooth curves. All right, so a little bit more calculator work real quick. We'll work on the idea of intercepts, if we're asked to approximate intercepts. Just make sure that you are reading the instructions. If I say find intercepts, I mean algebraically. If I say approximate intercepts, then you're free to use the calculator to tell me about where you think they are. All right, so we'll start with 3x squared minus 42x minus 3y is negative 192. So our calculators are programmed to work with an input variable and an output variable. They want the input variable to be x, they want y to be the output variable. In other words, they want that y sitting by itself. So I'll add 3y to both sides, and I'll add 192 to both sides. So now we have 3x squared minus 42x plus 192 is worth 3y. We don't have a 3y equals key, but we do have a y equals key. So we'll divide both sides by 3. We're kind of used to seeing the y on the left-hand side, so I'll go ahead and move that over. So 3/3 is 1. 1x squared is just x squared. 4 and 2 is 6, so 3 goes into that as well. So 3 goes in 4 once with 1 left over. 3 goes in 12 4 times with nothing left over. And let's see, 1 to 9 is 10. 10 and 2 is 12. 3 will also go into the 192. So 3 goes into 19. That would be 6 times with 1 left over. 3 goes in 12 4 times with nothing left over. All right. So we go to our y equals. We clear out any old functions that we have in our y1. There we go. All right. Trying to get the balance of the light without the glare. All right. So I think I've got that about as good as I'm going to get. So x squared minus 14 times x plus 64. And here I've not tapped hard enough on the 1 key. If you don't want to type everything over, second and insert is above your delete key. That will let you key in a figure and push it over rather than overwriting it. And we're going to go back to our Zoom 6. And on this one, so we're not seeing the graph at all, we can go to our table. So we'll go to the table set, We'll just start it arbitrarily at 0, delta table 1. We'll put the independent on auto for now, and second and table, and we'll look at where our values are. So it's looking like this one comes down, and it doesn't look like it dips back down to 0. So in some cases, there are no x-intercepts. In a later section, we'll see how we can figure that out algebraically. So another one we can check out where we will have some intercepts. And again, we'll see later on how to do these algebraically. We'll try out y is, let's say, opposite of x squared plus 15x plus 21. So again, back to our y equals. We'll clear out our old functions, and opposite, make sure you're using opposite, not your negative, or not your subtraction button. Opposite of x squared plus 15x plus 21. We'll start on zoom 6 and adjust as we need to. Okay, so we can see part of our graph, but not all of it. So again, we can go to the table and kind of get an idea of what's happening there. So it looks like our values dip down. So they're coming up from the -10, coming up, coming up, coming up. And then we start coming back down a little bit after 10. So 17, we're down at -13. So our window, instead of x's being from -10 to 10, maybe we'll set it -10 to +20. We'll count those by, oh, let's say 4s, or no, 5s. We'll use a nice, neat 5. If we're looking just for intercepts, if this is the same instructions of approximating intercepts, I don't really need to see the top of the graph, so I can leave the y's alone if I'd like. If you want to see the full thing, obviously you can just sort of check in with these. It looks like they are topping out in the 70s. If you'd like to see the whole thing, we can set the y max up to maybe 80 and count by 10. Okay, so now we can see our whole graph. We see there's 2 places it hits the x-axis, so we're going to have it calculate something for us. So second button, that's your yellow key here, second and calculate, and we wanted to calculate the 0. So left bound, we're going to move that cursor until we are